thank you very much to all the organizers, Aline and Mike, for giving Peter and myself the opportunity to present this work. Yes, this is part two. So, yeah. Let me remind you what happened last time. Peter overviewed our proof of the theorem that if you start with a finitely generated infinite commutative ring, the Hilbert 10 problem over R is undecidable. So the way this theorem was deduced from a theorem about number fields. And the theorem is that if you take any number field, then the integers, the usual integers, are the projection of the zero set of a polynomial in maybe many variables over OF. So you take a polynomial with coefficients in OF, you look only at the first coordinates of the zero set over OF, you project, and you get exactly the integers. And Peter explained how essentially, to the work of many people, you deduce theorem 1 from theorem 2, and then he went on and he essentially reduced the work to our main new contribution, which was this theorem 3, which is a theorem about the F-Antine stability. So if you start with a number field having at least 32 real places, then you can find an elliptic curve with a positive rank over the number field, and the rank is unchanged. So let me stress that this is a combination of independent work of Poonen and Shlapentokh, and also a trick invented by Shlapentokh that reduces essentially the proof of theorem 2 to a theorem of this shape. So you can find in Peter's talk the details of this surprising reduction. So the goal of this talk is explaining theorem 3 essentially. So you might wonder how do we prove essentially theorem 3? The reduction to that was explained last time, and also there is this funny condition on the 32 real places. So what is going on really here, and like why did we have that assumption? And yeah, so basically last time you got also some kind of high level overview of the proof of theorem 3. Today, we are gonna go a little bit more on the details of this theorem. So again, this is the theorem, K is a number field, 32 real places, and the imaginary extension Ki over K. There is an elliptic curve with rank unchanged and positive. So we will dive into the proof of this, into the main steps, and I will also announce a new version of the method, which is the following result, which will be uploaded on the archive today. And this was obtained independently with a different method by David Zivina, and also his paper will appear simultaneously. And the result is old open question that if you have a number field K, there is always an elliptic curve defined over K where the rank is exactly equal to 1. So it has a similar flavor than theorem 3. And there is a positive and constrained request on your rank. So your rank is positive, and here it's exactly 1. And our actual main theorems differ from our work and the one of David. And our actual main result is the following, and it essentially states that if you start with what looks like a random elliptic curve with full two torsion, and we'll define generic in the next slides, but for most elliptic curves with full rational two torsions, you can find infinitely many twists for which the rank is exactly equal to 1. So it's a slightly more precise statement, where in the quadratic twist family, where it is expected that the rank should be, according to parity, always the smallest possible value allowed by parity most of the time, but it is not known presently without BSD whether even there is a single twist with rank 1. So this result says that most of the time that's the case. The condition of generic, it's explained here. So it essentially means that there are enough places of split multiplicative reduction. So your model is given by this equation where A1, A2, A3 are integral, and essentially I'm asking that for every pair of roots, A1 and A2, let's say, there is a prime that divides with odd multiplicity A1 minus A2. It doesn't divide A1 minus A3, and therefore also A2 minus A3. They're congruent modulo A1 minus A2. And I'm also asking that A1 minus A3 is a square modulo P, and this prime P has some extra conditions that you find on the slide. So most of the curves have this property essentially. Yeah, sorry, this is the second property was missing there. And for 100% of the choices of A1, A2, A3, you can find three such primes for every pairs of roots. So this is what generic means. And so let me recap the situation. We have two theorems, and they are fairly similar in spirit. The first theorem was from our first work in 2024, where we proved that for a number field with at least 32 real places, you can find an elliptic curve with positive and unchanged rank over the imaginary extension. The second theorem is basically today is that for most elliptic curves with full rational two torsions, you can find infinitely many twists with rank exactly equal to 1. Okay, so these are the two theorems, and I will focus mostly on theorem A, and I will tell you what are the main novelties to pass to theorem B, and that will also give some light on these 32 real places. And somehow how we use them in the proof, how we remove them in theorem B. Notice that there is no assumption on the number field in the second theorem. Okay, so that's the plan. And let me start straight away. We have to construct an elliptic curve. It has to have positive rank, and there should be some constraint on the rank. In the first theorem is that it doesn't change in a quadratic extension. The second theorem is that it does not go beyond 1. So let's start with what Peter told you last week, and I will just tell you from scratch the family. The family is that we start with a curve, maybe it fails everything we want, and we start quadratic twisting the curve, but we twist by the values of the very same polynomial that defines the curve. So that's our pool where we are trying to pick up a favorable curve in this pool, and it's written in such a way that it comes with a point served on the plate, and the point is x equal n and y equal plus or minus 1. So that's an obvious point on your curve. And a point that Peter made last time is that you can really run over any n, despite the notation might suggest that n is in OK, you can actually run over any n in K. So once you write it as the ratio of two integers, then this is then a simple rewriting, but it's actually, I call it homogenization trick. It took us actually quite some time. We tried to work for a while with specialization in OK, and with n is in OK, we realized only quite later on that you can do this, and this increases quite a bit your flexibility, because now your twist is still as this tautological point, but if I multiply everything by d to the 4, I can absorb d to the 4 in y squared, and I can give a model where instead of f of n, I'm twisting by the value of this homogeneous form of degree 4, which is the product of 4 linear factors. So this is a completely trivial rewriting, this homogenization, but it will be extremely important later in the proof. And Peter already explained last time why that is so important when we will stare at the prime factorization of this product of 4 linear forms. So we have two demands on this curve. So we can choose our favorite n, and we have to guarantee two things. We have to guarantee that for theorem A that the rank is positive, and I already write something that was already mentioned last time, and I will explain it later. This second condition in red is the condition that the rank of minus the twist is 0. And that's not obvious that that is the same as the condition that the rank doesn't change. And I will explain it in the next slide. But then there are two demands for B, which are written in a bit of a funny way. I'm stating that the number is equal to 1, an integer, by stating that is positive and is not bigger than 1. So, but that is really how the proof goes. The proof there are two components in the proof. One is to make sure that the rank is positive, and one does something completely different and makes sure that the rank has an upper bound. So yeah, in both you see the similarity between the two situations. In both situations, you have a source. You need a source of lower bounds, and you need a source of upper bounds. So in one case, is an upper bound on the rank of this minus curve, and the other case is an upper bound for the rank of the same curve, which should be at most one. Okay, so let's keep it in mind. Let me explain this minus here, rank of E0 minus f of n. Why I put a minus? Why is this related to the Diophantine stability situation of theorem A? So what we really want is that the rank doesn't change in a quadratic extension. So why I put the minus? There is this classical result that the rank over a quadratic extension always decomposes as the sum of the rank of your curve plus the rank of the twist by the very same number of which you are taking a square root. Here, I remember is the square root of -1, so this is a more general decomposition. For every quadratic extension, you have a similar thing where the second summand should be E alpha, where alpha is the thing giving you the quadratic field. So this is a classical result, and the proof is not very hard. It's simply the following observation that if you take inside of E of ki, you take the minus point, so the one where this conjugation element sigma of the Gauss group acts as -1. So this is the 1 plus sigma torsion, and you take the multiples of 1 plus sigma, so the norm points, the points that you sum a point with the conjugate. And then on the left, you can basically recognize, if you write what sigma does and what -1 does on an elliptic curve, you will see that these are basically points whose coordinates are, one is rational and one is purely imaginary. So if you square I times y, you will get minus y squared, so you get exactly a quadratic twist. So the first guy is exactly the rational point. After an identification, it becomes a rational point on the quadratic twist, while the second guy is sandwiched between 2 times the rational point and the rational point. If you norm something, it becomes rational, and if you start with something rational, you double when you norm. So it has the same rank as the rational point. So the rank of the thing in the middle will be additively decomposed as the rank of the first term of the sequence and the second term of the sequence. So this explains this decomposition of the ranks. So the demand that the rank are equal can be rephrased by saying that the difference rank, the rank of the twist, is 0. So that's why we have, let me do a recap. That's why for theorem A, in our pool of curves, we are looking for a curve where the rank is positive, but the rank of the companion curve minus Fn, that rank should be 0. So while for theorem B, we are simply looking for something with rank 1. Okay, so let's start getting rid of the first one because we have already done quite some progress. We at least have a point on our curve. So the point n comma 1, the only thing you need to do now is to check that this point is non-torsion. And surprisingly, this is not the hard part of the proof. Like this family is really served very nicely with most of the choices of n giving you something having actually positive rank. The hard part will be the second red condition. So let's go get rid of this first one. Are there any questions so far? Please interrupt me for anything unclear. Okay, so let me explain why this is non-torsion. So this is the tautological point n comma 1, and the claim here is a very general claim that more generally, if you start with an elliptic curve with 0 and you start quadratic twisting, in the quadratic twist family, if you look at the torsion of the rational points, only for finitely many twists, you will see more than the 2 torsion, than the trivial torsion. So this means that for most choices of a twist, you will see only the trivial torsion points, which are y is 0 and x is a root of the polynomial. And you clearly see that this is not a point of that form. So if we achieve that, it basically means that we have to avoid a finite collection up to square for f of n, and that would be completely fine for us. So This claim clearly would be really good, and we gave in the paper a complicated proof of this claim using Morel's theorem, class field theory, and other things. And the referee very kindly found a completely elementary proof. And the argument is simply the following: you you map the rational point on the twist, just as we did before for d equal -1. You can identify them with the minus point of the square root d points. And it's the same computation we did before. And here there is a typo, sorry, this should be the image phi d torsion. So you should restrict to the torsion. So if you take phi d restricted to the torsion, then you will see that the image of all these points, of all the torsion of ED, is contained inside the torsion of your fixed elliptic curve. This is a set of bounded height because it has canonical height equal to 0, and that's off by a constant with the classical height, but it has also bounded degree. Each point here has degree 2. So by Northcott, it's a finite set. So after you map them inside the curve by multiplying by root d y, which is this identification between the rational point on the twist and the minus point on the quadratic field, you get just a finite set. And all you need to check is what happens when now you take different square free numbers, d1, d2. You have to check if you can get the same result. And that happens exactly when they hit the two torsion. It's a fairly straightforward check that if you take a point for 1d1 and a point for 1d2, and d1 and d2 are different, the only way you can get the same result in EK bar torus is that they were actually two torsion. So outside of the two torsion, you are in a totally finite set. So therefore, it follows the finiteness of the claim. So that's actually fairly elementary reason, and you have in total this claim, which clearly give us that for most choices of n, f of n will have no the point we constructed is not to torsion, and therefore is not torsion at all. So the rank is going to be positive. So I'm going to use green for sort of progress, and red will be still what remains to be done. So let's recap our situation. We have a pool of curves. The pool is this f of n, y squared is f of x. And we have two demands. One is the positivity of the rank, and one is a constraint on an associated rank, either the rank of the companion curve or the rank of the curve itself. So we still have to make progress on the upper bound. We have now made sure we have this claim from before gives us quite a lot of control on making sure that the rank is positive, but we still need to understand how to upper bound the rank. And so how do we attack those conditions? The main idea is that there is an explicit upper bound for two torsion for the rank coming from two descent. And, there are many types of descent. You can do 3 descent, 4 descent, but in a quadratic twist family, it is understood since at least the work of Zwirner and Dyer, if not before, that two Selmer, two descent is something extremely explicit. So let me improve the recap. So the new recap is that we substitute the conditions from the previous one. You see that the upper bound on the rank. Now I put an upper bound on the dimension of the two-Selmer group. I will remind you what two-Selmer is. It was defined in the last talk. I will give you slightly different but equivalent definition. And I am now reformulating our situation by, in the first case, by saying that two-Selmer is two-dimensional, and in the second case, by saying that two-Selmer is basically three-dimensional. So you saw already in last talk, but that it's something we will see again, that the rank is upper bounded by the dimension of two-Selmer minus 2. So the rank equals 0 becomes two-Selmer is 2, and rank equal 1, at most 1, becomes two-Selmer is 3. So this two-Selmer is whatever, if you have not seen it before, we will redefine it very soon, but whatever it is an upper bound for the rank, and the progress now, which is we just found a sufficient condition for the rank to be small, is that at least now the quantities in red are computable quantities. This was a point made also last time. The rank at the moment, unconditionally, we have no sort of algorithm to provably compute it, while the situation for Selmer groups is much better. So this is at least something explicit, but the problem remains, how do you enforce it? So it is something explicit, but maybe you have no idea how to control these quantities. And the rest of the talk is focused a lot on this question: how do we still manage to gain some control onto Selmer to get it down to these numbers? So let me begin with the most basic point. What is really this two-Selmer space? So the space of which I'm taking the two torsions. So let me briefly remind the situation. So let me define two-Selmer for an elliptic curve. Here I take ABC again, if you like, really, in the ring of integers of K. And two-Selmer really defined in a most elementary way. You found last time more cohomological description. Here is an equivalent description. You can define a map that takes two points on the curve x comma y and sends it to x minus a, x minus b. That's it's our map, but it turns out you can even check it explicitly. This map for x different from ABC, it's a well-defined map in K star modulo squares when you take your point modulo doubles. So it defines an injection actually of the rational points modulo doubles in K star modulo squares. So it's a fairly concrete map. And in the point A and B, you have to be a little bit careful because you get 0, so that's not in K star. But you can notice the simple trick is that x minus a up to squares is the same thing as x minus b times x minus c. That's the equation of the curve. It's somehow tautologically the case. So you can always move out of the 0, and that defines the map for the two torsion of two Selmer. So you send x comma y in x minus b, x minus c. So a minus b, a minus c, and b minus a, b minus c. All right, so this is the beginning of the story, and the disappointing news is that you started with something which should be finite, that you want to upper bound, and you are mapping it into an infinite dimensional space. So you want to find some reason to have some control on this thing, and since you have no idea of who the rational points of the curves might be, and that's the point, you start with the less ambitious demands, which it's a trick you often do in number theory. When you don't know the total points of a variety, you start studying at least the things that are locally everywhere of that form. So two Selmers, you take the pairs of numbers that have at least a chance to come from EK modulo 2, because they come locally everywhere from the same construction on local points. So for every place of your number field, you have the same map, and you demand simply to land in that local space for every prime place P. Okay, it turns out that that is quite a constraint, because you can check fairly easily using elementary things about elliptic curves that the image of this delta will have always dimension half of the dimension of the total space. So you're landing in something that has half dimensional in the total space of local numbers up to squares. And furthermore, it's very explicit what is the support. If the prime doesn't divide the places of bad reduction, basically you cannot have odd valuation. So the pairs of square free numbers that you get are supported only in primes that are either even or have bad reduction. And these you can really even see quite elementarily from the definition of the map. If P doesn't divide, say, A minus B or A minus C or B minus C, then if you have odd valuation there, you have no chance to solve this equation, just because you will not make it into a square. you will not compensate from the other factors. Essentially, this is where it comes from. So this is something that you can also revisit in that more cohomological point of view that was given in the last lecture. But in one way or another, the good news is that this two-Selmer is a bunch of pairs of square-free numbers that are supported only at the places of bed reduction of your curve, and maybe two. And furthermore, that means that when you start quadratic twisting your curve, well, the places of bed reduction, the new places of bed reductions are now the old ones plus the prime divisors, the odd prime, the things that divide with the odd multiplicity d, the primes that ramify in k root d over k. So you have very good control where to look for these square-free numbers, but that leaves you still with a lot of possibility. And therefore, you want to study more precisely at these primes what are the constraints. As I mentioned in the previous slides, you land in a half-dimensional space. So here, the dimension is always half of the dimension, and you can be very precise for an odd prime that divides d. Yeah, p here should be also odd. So p should not divide 2 times delta e, and p divides d, let's say, then you can be completely precise on what is this local Selmer. So this is in a total of a four-dimensional local space of local numbers up to squares. You are in the linear span of these two numbers, where alpha, beta, and gamma are basically the differences of the roots labeled in that way. So it's a very explicit space, and it's a constraint for your pairs of square-free numbers, which you can organize as a fairly complicated matrix of Legendre symbols, of mutual Legendre symbols between the prime factors of 2D and places of bed reduction. So it's a kernel of an explicit matrix of Legendre symbols that you are trying to control. And so I promise it's something computable. Now you see that it's actually fairly computable. It's very explicit what the description of two-Selmer is. So let's make a panorama of our situation. We have made some progress on making the rank positive, but remember, we still have to upper bound the rank. We decided to upper bound with the dimension of two-Selmer. Two-Selmer is a fairly involved but explicit matrix of Legendre symbols in the prime divisors of your twisting parameter. And for us, the twisting parameter is the degree for homogeneous form in M and D, which is totally split, this product of four linear forms, D, M minus A1D, M minus A2D, M minus A3D. So up to 2 and delta of the original curves that are fixed, the extra primes that are in the scene, the extra actors of this situation are these divisors of four linear forms, of the product of four linear forms. So the notation here is that N is M over D. We have homogenized, remember, and we get this situation. So we have this matrix of Legendre symbols, and I will not tell you explicitly what it is, and I will tell you essentially what we have to do about it in a later slide. The Selmer is basically the kernel of this matrix. So essentially what you have to prove is that within the possible ranks that this matrix might possibly have, you have to prove that the matrix is basically almost invertible. So this matrix will have a systematic kernel of dimension either 2 or 3, depending on theorem A or theorem B. And you have to prove that basically there is nothing else. So you have to prove that within some obvious constraints, there is no extra element in the kernel. So basically you want to make the columns of this matrix as linearly independent as possible. Remember, they are all Legendre symbols in the divisors of this product of four linear forms. Well, how do you do that? So how do you even control the product of prime divisors of the four linear forms? And that was the idea that Peter introduced in the last lecture. The idea that we use is, well, at least let's start getting control on the prime divisors of this product of four linear forms by invoking results from additive combinatorics that are able to prescribe that these numbers are either primes or almost primes. So that's the high-level idea. And so let's see a little bit how that plays out in our situation. So we want this matrix M of Legendre symbols to be almost invertible. And the first thought you might have is, okay, I'm going to make them prime. So I'm going to make them, each of them just prime. And I'm going to invoke a result of Bataru Kai from 2023, where he extended a classical theorem of Green, Tau, and Ziegler to number fields. And on some mild assumptions on A1, A2, A3, you can make sure that simultaneously all these numbers are prime. This might be your first thought, your first instinct, and there is already a problem. So this is a matrix of Legendre symbol in the things in the first line. And there is a submatrix that is not up to you, that comes from your original choice of A1, A2, A3, from E0. And it's some minor that it's outside of your control. And as far as you know, it could contain most of your prime factors. If you choose to make the rest only with 4 primes, then this could contain 1,000,000 prime factors. So now you have a matrix which is completely dominated by the part of bad reduction. And this matrix could have a massive nullity, very, very low rank. So if this matrix has very, very low rank and you add just 4 rows to the matrix, there is no way you're going to bring it down. So you need something else. So the second thought that you can have at this point is, okay, I'm going to introduce a number which only depends on the original elliptic curve, kappa of E naught, some explicit square-free number that sort of I put in one of these 4 linear forms and as the task of reducing the rank down to something manageable so that I overcome the first problem, that when I do 4 more steps, I can go to maximal rank. So you plan to introduce this number kappa, which has this role basically. And the way we proceeded, and I think it's more or less the same, but it's a bit more complicated actually if you put it in other places. So you can put the number, let's say, in D. So you would say kappa now divides D. Yeah, so let me recap a little bit the situation. We have this matrix of Legendre symbols in the prime divisor of the 4 linear forms and delta, and you want to make it almost invertible. And our second attempt is to make m minus a1d prime, m minus a2d prime, m minus a3d prime, and the parameter d is not exactly prime, but it's a fixed number which only depends on the original elliptic curve times a prime. And okay, with a little change of variable, rewriting your forms in a different way, you can still invoke Kai's work and make sure that you can have this. The point of this parameter kappa is to compensate the original potential high nullity of the matrix on the really bad places, the places of bad reduction of the original curve, the minor coming from there. Okay, however, there is a second bad news, which was mentioned also last time, that we have no control on the symbols Qi over Qj. So additive combinatorics simply doesn't tell you what these symbols are. And if you do some simple manipulation of adding and subtracting one from the other, you will see that up to something fairly controlled, all these symbols are coming down to a single dark symbol, which is M on D. So you have 4 linear forms in M and D, and you want also to have control on the Legendre symbol of M on D, and there are no results like this. So then you could think, okay, my situation is pretty bad. I need a matrix of Legendre symbol, and this 4x4 is completely uncontrolled, and I can control all the other symbols, but this 4x4 is out of control. So here is then the next thought is to use what people call matrix rigidity. So I didn't know this was actually a thing. So I was told last week here in Max Planck that there is a whole field called matrix rigidity. In our case, will become something fairly explicit, but is this general idea that sometimes if you arrange your matrix outside of this dark 4x4, let's say, corner, favorably enough, no matter what happens in that corner, the matrix stays invertible. Somehow that corner cannot anymore affect the linear independencies of the column. So this is a general idea, and in our case, it will come down to something very concrete. So that is how we are gonna prevent Qi and Qj to be on our way. And I can tell you essentially what that comes down to in our case. So this we extrapolated this from the work of Klagsbrun, Mazur, and Rubin, which have some sort of very spectacular general description of 2-7, a very broad set of cases, which in particular in our case tells us that if you really want to avoid the knowledge of these symbols, essentially there are not many other options than making sure that before the 4 special primes given by Chi, by additive combinatorics, the remaining minor has dimension 6. And not only that, if you take the numbers that are coming from that minors, which are pairs of square free numbers only supported at this prime, so they're before the primes coming the Q1, Q2, Q3, if you reduce the kernel of that minor modulo these numbers, you should get an isomorphism. So it should be a 6-dimensional space that reduces maximally modulo Q1, modulo Q2, and modulo Q3. It takes a lot of theory to explain why that is the case. For now, just trust me that this is essentially the output. To arrange this matrix in such a way that the final 4x4 minor of the additive combinatorics primes doesn't matter, basically means that the pre-additive combinatorics primes, the one coming from this minor, should give you a matrix of kernel which is 6-dimensional, and the kernel should reduce maximally modulo Q1, modulo Q2, and modulo Q3, modulo squares. Okay, so this makes sense because these are divisors of these numbers that are co-prime to Q1, Q2, Q3. So you can reduce them modulo Q1, Q2, Q3, modulo squares, and check whether they go everywhere, basically. And the only information that this requires is knowledge of how Q1, Q2, Q3 reduce modulo these fixed numbers and also their behavior at infinity and 2. And this will come back very soon. And this is the 32 real places are starting to come here. And here there is a third problem, which is quite upsetting, is that Q1, Q2, Q3, by the very way you set it up, they reduce to the very same number modulo everything else, basically, modulo this auxiliary number kappa, because remember, we wrote D as kappa times a prime, and then you have Q1 is m minus a1d, Q2 is m minus a2d, and Q3 is m minus a3d, but kappa divides d, so Q1 is m modulo d, Q2 is m modulo d, and Q3 is m modulo d, so in particular modulo kappa. So these 3 primes are all the same modulo kappa. However, you are asking here something which is upside down. You are asking what divisors of kappa do modulo Q1, Q2, Q3. That's not exactly the same thing, and this is very important. So, but this is somehow, there is a contrast here. There is a conflict. On the one hand, Q1, Q2, Q3 have the same behavior modulo kappa. On the other, you would like some divisors of kappa to behave very differently modulo Q1, Q2, Q3. So it almost feels like you are running into a contradiction. And here is where the real places come. And the idea is that, well, you want divisors of kappa modulo Q1, Q2, Q3, and all you know is that Q1, Q2, Q3 are constrained modulo divisors of kappa to be the same thing. But when you swap the quadratic symbol, that's not a perfect symmetry. Like you cannot swap quadratic symbols and expect that you always get the same result. There is a price to pay. And that price to pay depends on the behavior at the infinite places and the two-adic places. So I will give you a toy example in a second, but essentially if you arrange if you use the real places favorably enough, this superficial constraint, when you swap it, is not a constraint anymore. So let me expand on this idea, how you use the real places to swap the Legendre symbols and get essentially in a situation favorable for theorem A. Here is a toy example. So imagine Z1, Z2, which you can imagine as the part coming before Q1 and Q2, Q3, the part supported in kappa. They are take Q1 and Q2 that are both squares modulo, let's say, kappa. So in particular, Q1 and Q2 are squares modulo Z1 and Z2. On the other hand, you maybe want to still say that Z1 and Z2 are very different modulo Q1 and Q2. Now, suppose that I tell you that Q1 is negative at one infinite place and positive everywhere else. And I say that Q2 is negative at the first infinite place, positive at the first infinite place, and negative at the second infinite place, and positive at all remaining places. So they sort of are in two different infinite places. And suppose that something similar is happening for Z1 and Z2. So sort of Z1 is support as a sign at infinity 1 and no other sign, and Z2 likewise. And what happens now is that when I apply Hilbert reciprocity, the fact that Qi and Q1 and Q2 are both squares modulo Z1 and Z2 doesn't prevent Z1 and Z2 to have a very different behavior modulo Q1 and Q2. So Z1 is a non-square modulo Q1 and it's a square modulo Q2, while Z2 is a square modulo Q1 and it's a non-square modulo Q2. So you see how the infinite places can still allow you to swap differently Legendre symbols. So the fact, going back here, the fact that your linear forms constrains Q1, Q2, Q3 to have the same residue modulo kappa doesn't mean that divisors of kappa are gonna be constrained in the same way modulo Q1, Q2, Q3, exactly because of this kind of computations here. This is just a toy example with just two numbers. You can imagine with a vector of 6 sort of pairs of numbers, so 12 numbers with 6 infinite places going on. It's much more complicated. You find the table in the paper, but essentially the starting point is apply as many times as possible these kind of ideas. So that's the next thought. To defeat this constraint, you use the real places. So this is exactly where these 32 real places come into the game for theorem A. And then you might ask, okay, what about theorem B? Theorem B is now a general elliptic curve, and it's about the elliptic curve over a general number field, and there is no condition on the number field to have 32 real places. So how do you deal with that? So this is the next problem here, and the way we found to get around this is to exploit places of split multiplicative reduction, and that's where this definition of generic comes into play, to mimic what is going on with these infinite places. And so let me be a little bit more precise. So while M minus A1D, M minus A2D, and M minus A3D have all the same congruences modulo any divisor of D, namely just M, there is no, if kappa divides D, kappa is coprime here, this auxiliary number is coprime to the places of bed reduction of your curve. So you still have a potentially different sign modulo these primes of bed reduction, and you don't have a constraint modulo those primes. So our starting observation is that one, and we found a way to set up a complete analogy where these Archimedean computations are completely simulated by the places of bed reduction, and they have a non-Archimedean version. And essentially, that's where the assumption of being generic comes in. You need two places from every A1 minus A2, A1 minus A3, A2 minus A3. But for some other technical reason, we raise it up to three such primes. So places of split multiplicative reduction are essentially replacing the 32 real places. And that's what happens in the proof of theorem B. And the upshot is that now we are in good shape. We have a pool of curves where most of the time they have positive rank, and with additive combinatorics we manage to control the rank of this matrix of Legendre symbol to make two Selmer as small as possible to exactly match the constraint demanded by both theorems. So let me make maybe also here a very brief point that I was a little bit imprecise that I said only that you have to avoid finitely many numbers up to square to guarantee the first condition. You see from the way we constructed these twists f of n that they are changing supports on their product of four primes, and these four primes are moving. So we will certainly avoid a finite set modulo square. So the first condition is also guaranteed fairly easily by the additive combinatorics construction, and especially the second one is where this additive combinatorics goes into the game. And let me use the last 3 minutes to summarize what we have learned here. So the summary here is that it is not too difficult to construct curves with positive rank. There are a billion possible constructions, and the one we use is perhaps a sort of a very simple-minded one that you start twisting by values of the polynomial itself that has points, which we explained why they are most of the time non-torsion. So that is not too hard to have things with positive rank. And also having upper bound on the rank of a given curve is not too hard. That there is descent. But what was open for a long time is how to achieve simultaneously both things, how to have a situation where you construct a point and you guarantee that there are no further points. And uh, yeah, so there was no bridge between these explicit constructions of families of curves with positive rank and the world of descent and upper bounds on the rank. So our method that we introduced in this first work in 2024 has been to bridge these two worlds using additive combinatorics. And the reason is what you saw, that the primes dividing the discriminant of the curves are the ones important for descent. So it's the way to control primes value of a polynomial. One possible way, if you set it up favorably enough, is additive combinatorics. So let me just mention that after this, many people have used these ideas, and there are by now, by tomorrow, there will be at least other 3 works in this direction. One has been the work of Alpoj, Bhargava, Ho, and Schmidtman, where they gave an alternative proof, a very nice and elegant proof of Hilbert 10 by using, roughly speaking, the same broad strategy, and but on a slightly different family of abelian varieties, which sort of makes the inner mechanism of the proof rather different. And likewise, David Zivina proved that there are infinitely many curves over Q of rank exactly 2. So you see again, you want a positive but exact number on the rank using in a different families of elliptic curves in his case. Roughly speaking, the same bridge between explicit construction of points and descent given by additive combinatorics. So yeah, so I think this is all I wanted to say, and I'll stop here.